In this video, we'll take a look at some properties of horizontal asymptotes that you might be familiar with from a previous math class, and then we'll look at a couple more examples of infinite limits for some more difficult problems. So here we have a quick definition here. It says if the graph of f approaches a line with a finite non-zero slope as x approaches positive infinity, then that is called a slant asymptote or an oblique asymptote. So here I have an example of one. This is approaching, oops, wrong color. This is actually just approaching the line y equals x right here, so you can kind of see that. It's essentially just neither a horizontal nor a vertical asymptote here, and those will always occur when the degree of the numerator is exactly one more than the degree of the denominator. So here I have x squared and then x to the first in my denominator. As long as the degree of the numerator is exactly one more, you will always have an oblique or a slant asymptote here. As for finding them, it is a little bit tricky. This one wouldn't be too bad, but in the majority of cases, we would have to use polynomial long division. That's something that I'm not going to worry too much about, because we're just not going to do a whole lot with slant or oblique asymptotes. If you understand horizontal and vertical asymptotes, then that's good enough for me here. So really quickly, just some properties of asymptotes, of horizontal asymptotes, of rational functions. I'm going to fly through these pretty quickly because we've touched on most of these before, but these are just some shortcuts you might remember from a previous math class from college algebra. So here we have a rational functions, f of x equals p of x over q of x, and p of x equals blah blah blah, q of x equals blah blah blah. Essentially what I'm going to be paying attention to is this part right here. So in part A, it says that if the degree of the denominator, if the degree of the numerator is less than the degree of the denominator, so here I'm going to underline the degree of the denominator, that one's bigger, then in that case, the limit as x approaches plus or minus infinity is equal to 0, and y equals 0 is a horizontal asymptote. So that all occurs if the degree of the denominator is bigger. Remember, that means if you have a higher power of x in your denominator. If they are the same, if the degree of the numerator is exactly equal to the degree of the denominator, then the limit as x approaches positive or negative infinity is equal to a sub m divided by b sub n. And this, let me grab a different color here. This I always just refer to as the ratio of the leading coefficients. So you just take the leading coefficient of the numerator, divide it by the leading coefficient of the denominator. And then that same value, again, that's this guy right here, is a horizontal asymptote of your function. So if they're the same, then that's what happens. If, on the other hand, the degree of the numerator is greater than the degree of the denominator, then your limit as x approaches plus or minus infinity is either positive infinity or negative infinity, and in this case we have no horizontal asymptote. So this occurs if the degree of the numerator is again greater. Here, this part right here, part D, this is just summarizing what we mentioned earlier about slant asymptotes, essentially saying, hey, if the degree of the numerator is exactly one more than the degree of the denominator, then in that case we have a slant asymptote. I'm not going to ask you much about slant asymptotes. I just want you to be aware that those exist. I want you to kind of be able to identify them, maybe if you were to look at a graph. And then last one, part E, this is also review here. It says, assuming that f is in reduced form, then the vertical asymptotes occur at the zeros of q of x, essentially the zeros of the denominator here. And this is something that we talked a little bit about in the last section here. It just says, hey, if you want to find the vertical asymptotes, take the denominator, set it equal to 0. Wherever you have a 0, that's where you have a vertical asymptote. So you can, if you would like, refer to these three properties up here. If you would like to refer to these three properties, I'm generally okay with that, but I need you to explain your reasoning. So if I ask you to find the horizontal asymptotes of a function and you use one of these properties, I want you to tell me how you arrived at your answer. You can say, okay, well, this is a horizontal asymptote because the degree of the numerator is equal to the degree of the denominator, or you have to mention something about how you got to your answer. So I should see some sort of reasoning or explanation comparing the degree of the numerator and the degree of the denominator if you're going to use one of these three properties. Of course, you can fall back on your limits as x approaches positive or negative infinity, and honestly, I would encourage you to do that. I think it's good practice, and it's much more convincing than just saying, hey, I looked at the degree of the numerator and the degree of the denominator. So let's look at a couple more limits at infinity here. We're actually going to work with some radical functions, which are a little bit tricky, but I'll show you the tools that we need in order to deal with this. So here I have limit as x approaches infinity, square root of x squared plus 1 over 2x plus 1. So in a situation like this, I'm going to look at that and I'm going to say, boy, that looks an awful lot like a rational function here. So I'm actually going to take a very similar approach to this problem that I did for other rational functions. I'm going to look at the highest power of the denominator once again. I'm going to start off exactly the same way. So in this case, just x to the first power. That's what I'm interested in. So let me rewrite this so it's a little bit bigger. Limit as x approaches positive infinity, got radical x squared plus 1 divided by 2x. Oops, was that plus 1 or minus 1? Plus 1. Plus 1. And I'm looking at this guy right here. I'm looking at that highest power of x in the denominator. And I'm actually going to take the same approach where I'm going to multiply both my numerator and my denominator by 1 over that largest power of the denominator. The denominator is not really going to be any different here. I'm just going to take this, I'll distribute that to each term. That part's not going to be an issue. So my next step would be, okay, let's look at limit as x approaches infinity. My denominator is going to look exactly like you would expect it to. It's going to be 2 plus 1 over x here. My numerator, on the other hand, will present a little bit of a problem here because now I have something which is underneath this radical right here. This does not have a radical. How do I compensate for that? How do I deal with this? So what I need to do is I need to rewrite this guy right here that I'm multiplying by with a radical so that I can multiply these two things. So I'm going to think to myself off to the side, hey, if I want to think about 1 over x, that's really the exact same thing as 1 over x squared, or rather the square root of 1 over x squared. Right? Normally you would be going the opposite direction. You're normally trying to get rid of the radical, but we could rewrite it this way. You normally wouldn't choose to write it this way, but we could if we wanted to. And here's a case where we might want to here. We might say, okay, rather than writing that as 1 over x, I'm going to write that as square root 1 over x squared. And now I can multiply the parts that are inside of the radical. I can multiply these two parts. So in my next step, I'm actually just going to draw out this process just so we can see where we're going. So I have this x squared plus 1, and I can multiply this by 1 over x squared all under one radical now because everything that I've written in that numerator has that radical. And then after that, the rest of this problem is going to be pretty similar to rational functions. So I'm going to take this 1 over x squared, I'm going to distribute this to each part underneath my radical in my numerator. So I'll have limit as x approaches infinity here. I should have square root, let's see, x squared times 1 over x squared. I'll have 1 plus 1 over x squared. In my denominator, I've got 2 plus 1 over x. And at this point, I should be able to evaluate my limit here. Everything either goes to a constant or 0. So 1 is a constant. That's just going to approach 1. 1 over x squared here, x is approaching positive infinity, so 1 over x squared must approach 0. In my denominator, 2, well, that's a constant, so it stays at 2 plus 1 over x. I know that that will approach 0, so I have radical 1 over 2 will approach 1/2 here. So this worked out very nicely here. We were able to evaluate this limit using a lot of the same tools that we used for rational functions, and really just the new addition here is this rewriting that 1 over the highest power of x. It's rewriting that piece with the radical that's kind of new. Part B is a little bit trickier because that doesn't quite look like a radical. So here I have limit as x approaches negative infinity. Here I have x minus square root x squared minus 9x. And I'm going to end up with, you know, infinities, and it's going to cause a problem if I try and take this and either positive or negative infinity and plug this in. It's just not going to work for me. So what that means for me is I need to think about how I can kind of rewrite this. How can I make this look a little bit different so that it's a little bit nicer for us to work with here? So I'm going to think about this. Let me just rewrite this. Limit as x approaches negative infinity here. I have x minus square root x squared minus 9x. And I'm going to think about this as being over 1. All right, I can take any number divided by 1. It's itself. What I'm going to do is something most of you probably wouldn't think to do, because most of the time when we did this, we were trying to get rid of the radical in the numerator, in the denominator. But here I'm going to try and get rid of that radical in the numerator. I am going to multiply by the conjugate here. So I'm going to multiply by x plus square root x squared minus 9x, and then in my denominator here, I should do the same exact thing in order to keep this expression equal here. So x plus square root x squared minus 9x. So my numerator is a little bit tricky to deal with here. I've got limits as x approaches negative infinity here. My numerator, it looks like I would have to go and FOIL this out, and it would get really ugly and really long. But remember that when we multiply by the conjugate, let me change my color here. Really what I have is a minus b times over here a plus b. So I really just have a difference of 2 squares. So when I multiply those two, I'm going to have a squared minus b squared here. So when I multiply these out, let's see, if I square this first term, right? If I square x, first of all, that's my a squared. That should just be, well, x squared. Minus b squared here. B squared, let's see, b squared. Oops, lost my color. So here, b squared, b in this case is square root x squared minus 9x here. That's going to be my b squared. So if I square that guy, it's just going to drop the radical. So minus, and we'll want to be careful here. We want to make sure we use our parentheses. I should have x squared minus 9x divided by, in my denominator, I'm not going to worry about simplifying that at all, right? 1 times anything is itself. So here we just have x plus square root x squared minus 9x. From here, I see, okay, well, I have x squared minus x squared. These two cancel, so minus negative 9. I've got limit x approaches negative infinity here. I've got positive 9x divided by x plus square root x squared minus 9x. Here in this case, we are going to take almost the exact same approach we did in the last one from the rest of this problem on. So hopefully we look at this, we say, boy, this looks an awful lot like a rational function. This looks sort of like a rational function with the exception of course, this radical right here. So think back to what we did in the last problem, right? We just found that highest power of the denominator and we multiplied that through. So I'm going to see if I can pull that same trick right here. Now you might have a little bit of hesitation, and rightfully so, about what is the highest power of the denominator. In this case, I would look here, I've got an x. Here I would look just at this part right here. Really, I have square root of x squared, which would just be x. So I'm going to think to myself, okay, let's try taking this. I'm going to multiply both my numerator and my denominator by 1 over x. Let's see if this works. So for my numerator, let's see, 9x times 1 over x, so I should have limit x approaches negative infinity. Here I should just have 9 in the numerator, that's good. In my denominator, let's see, x times 1 over x, that's just going to be 1. Plus, here, again, this guy right here presents a problem, right? I have this radical, and then I have something else which is not under a radical. So maybe instead of multiplying that by 1 over x, I can again pull the same trick I did last time and say, okay, what if instead of 1 over x, I think about that as square root of 1 over x squared. And then I can take this piece and distribute that to each part here, because now it's under a radical as well. So oops, let me keep my red actually. So here I'll have square root x squared times 1 over x squared. I'll just have 1 minus 9x over x squared. I should have 9 over x squared. And then from this point on, everything is either a constant or it will approach 0, which is exactly what I want. So we should be able to evaluate this limit here. So this says limit as x approaches negative infinity. And actually, oops, we're going to evaluate this limit x, so we don't need that statement. So here, 9 is a constant, right? So 9, that should approach just 9. Doesn't depend on x in any way. Next, I've got 1. So, okay, that's a constant. That will approach 1 plus radical. Here, I have another constant, 1. So 1 should appear under my radical. It doesn't depend on x in any way. And once again here, whoops, I've got 9 over x squared this time. So here I have a positive power of x in my denominator. My numerator is a constant. So that particular term must approach 0. After this, just a little bit of calculation. I've got 9 over 1 plus radical 1, which is 9 over 1 plus 1, gives me, oops, 9 over 2 here. So just be extra careful when you're working with radicals. Make sure that if you're going to use this same technique when we're evaluating limits at positive or negative infinity, we do need to have this extra crucial step of rewriting that 1 over the highest power of the denominator so that it has a radical. We have to make sure we do that here if we're going to have any sort of success with this technique.